Lakeside Kids is supported by Dane County Arts with additional funds from the Endress Manufacturing Company Foundation, the EVU Foundation Incorporated, charitable arms of the Capital Times, the W. Jerome Frautschi Foundation, and the Pleasant T. Rowland Foundation. And now, the physics experience. Take it away, Mike.
Thank you, Heather. Good morning, ladies and gentlemen. Hi, my name's Mike Randall. I'm the president of the Physics Experience. You may have guessed from the name of the show, The Physics Experience, that we're going to talk about physics today. We're going to talk about what it is, what it has to do with you. Mostly, we're here to have fun today. Are you okay with that? And if you like what you hear, do this. Now, some of it, I know, even if I don't see you at home, I've got a few people that are going to be helping me out today, and I can see them waving their hands, so I know that I'm doing something that you like. Okay, the way the show is going to go today, we'll do talk about a few things up front just so that we can get started with this. But I'm going to have my helpers choose different demonstrations, and we're going to demonstrate those, whatever they want to see. Now, I've got lots of things to cover today. I've got a hovercraft, I've got cannons, I've got high voltage electricity, I have lasers, I have liquid nitrogen, I got all the good stuff and a lot more. So we're going to have a ton of fun. And then remember, keep those questions in mind, because at the end, last 15 minutes or so, I'll be doing a Q&A session. So if you've got any questions at all about any science topic, if I don't know the answer, I'll tell you so. But we're going to have fun. Okay, so let's get started. Let's choose a demonstration. Oh, you know what? Before we do that, sorry, I almost skipped over a step. So if we're going to talk about physics, shouldn't we know what physics is? So there's a lot of different ways you could look at physics. But the most important, here's my definition of it. Physics is the study of stuff. Yeah, like this room is made out of stuff. It's full of stuff. I'm made out of stuff. You're made out of stuff. We're all made out of stuff, but scientists have a different word for everything. Scientists don't call stuff stuff. Scientists call stuff matter. Matter. On the count of three, I want you to all say it with me. 1, 2, 3, matter. Perfect. So physics is the study of stuff or matter, okay? Wait, that's not all. There's more. Physics is also the study of how you move stuff around. What gives you the ability to move stuff around? It's a one-word answer, starts with the letter E. Oh, I think somebody said it. Energy. Energy is the answer. Energy is the ability to do work. Energy is the ability to do anything. So physics is a study of matter and energy and how those two things play with each other, how they interact. That covers a lot of stuff. It covers movement, like throwing a ball. It also covers sound you can hear, light you can see, heat you can feel, electricity, magnetism. And then a whole bunch of other stuff that's very important in our lives called modern physics. And I'll give you a really cool demonstration of that later today with lasers. Okay, now let's choose someone. Who's going to help me out first? All right, go ahead and announce yourself once you're off mute. So Heather, are you selecting him? This is what it looks like.
We have Adeline who would like to answer your question. She needs to unmute herself.
Hi, Adeline.
Can you unmute yourself, please?
Yeah.
There you go.
There we go.
Oh. We got a really good echo, but just tell me what you want to see.
I want to see the toilet paper cannon.
The toilet paper cannon. Okay. So I'm just going to kind of come over here. That's the toilet paper right there. But the cannon part is actually down here, attached to the hovercraft. So I tell you what, maybe we'll start off with the hovercraft and I'll move over to that too. Would that be okay with you? Yeah, I think you'll like this a lot. So in science, there are forces. A force, by the way, is just a push or pull. Scientists have a different word for everything. So scientists will call a push or a pull a force. And one of those forces that happens is friction. So if you put your hands together like this and rub them, they don't want to rub very well. There's some resistance. There's something that holds your hands back. That's a force called friction. Now, right now, you can see this gray board down here. There's a lot of friction between that board and the floor. So if I try and push it with my foot, it's really hard to move. But there's also an air blower attached to that board. And when I turn it on, the air is going to go underneath that board, and it's going to actually lift the board up just a tiny bit, enough that the board and the floor aren't touching anymore. Because see, friction only works when things are touching. So if they're not touching, what do you think is going to happen? It moves around really easily. You like my passengers? Let me bring this back up. There we go. Normally I have someone from the audience ride that, but you know, we don't have any kids here, so my wife has stuffed animals, so we had them give the ride. So that's really fun. By the way, those aren't hard to build, but you need adults to help you with tools, and there's no brakes or steering on it. So if you do it, make sure you got plenty of safety gear around. All right, now that we've done that, let me see if I can get this loose. Because I'm going to use the leaf blower for this. So this is a demonstration of something called Bernoulli's principle. Very important thing to know, and I've got a lot of demonstrations that are based on this. We are sitting at the bottom of an ocean right now. Right now, yes, you, all of you, you're sitting at the bottom of an ocean right now. And it's heavy. Now, it's not an ocean of water, it's an ocean of air. You know, the air on us is heavy. See the end of my thumb? It's about 1 inch wide and 1 inch high. Any place I could cover with the end of my thumb, the air is pushing down with the weight of a bowling ball. Seriously. So there's lots of bowling balls sitting on my head right now. There's lots of bowling balls sitting on your head too. But why don't we notice that? Well, the air pushing on this side balances out the air pushing on this side. So that kind of cancels out. We don't notice it. It's called the forces are in balance. But there's different ways we can unbalance those forces and really fun things happen. So notice in my toilet paper shooter, can you see how that's aimed? The nozzle's actually aimed to go over the top of the toilet paper. So what do you think is going to happen when I turn this on? Shall we find out? Oh, you should see my studio now. I should have probably saved this one for the last. And now I got to uncover my camera. Oh my gosh, it hung up way over here too. So this very smart guy named Bernoulli figured something out. He said when the air is moving faster, it doesn't push down as hard. So what that means is that the air's not pushing down as hard on top because of the way I had it aimed, but the air is still pushing just as hard underneath. That means the air underneath lifted this up and made it fly out into the room. Now, if any of you have ever flown on an airplane, you're very familiar with this because that's how an airplane works. In an airplane, the wings are curved on the top and they're flat on the bottom. So when the airplane wing goes through the air on top has to travel further, which means it's going faster. That means that on the top of a wing, the air's not pressing down as hard as the air under the wing. So it's the air under the wing that lifts it up. Now you know how airplane wings work. And you learned that from toilet paper. Isn't that cool? Great question. All right, who's next?
We have Emmeline, and Emmeline, can you unmute yourself, please?
Hi, Emmeline. There you go. Hi. So, what do you want to see?
The liquid nitrogen.
The liquid nitrogen, oh, one of my personal favorites. I tell you what, though, to get started here, we got to talk about what temperature is, okay? This is very important. You're made out of stuff, right? We already established that. Scientists call stuff matter. If you take any piece of ordinary matter and you start breaking it into smaller and smaller pieces, you eventually get down to some little tiny things that have a boy's name. So, do you know what I'm talking about? Starts with the letter A. Oh, I think you're back on mute, aren't you? You can stay off mute.
Atoms.
Atoms, very good. Sounds like a boy's name. So everything around us is made of little tiny things called atoms, okay? Way, 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 way smaller than these marbles, okay? Now, atoms can move around. So if we put energy into stuff, it can actually make those little atoms jiggle around. If you put a lot of energy in, they'll jiggle around faster. That is what we call heat energy. That's all that it is. Heat energy is how fast are the atoms in something jiggling around, okay? So you can add heat energy to things, you can take it away. So liquid nitrogen, I keep it in this special container. This is called a dewar. It's super, super insulated, which means that it keeps the heat energy from going into this bottle. I'm going to move my camera on here so you can see this a little bit more close up. Okay, that ought to do. So, if you take a lot of heat energy away from the air in this room, it turns into this stuff. That's liquid nitrogen. This stuff is crazy, crazy cold. 321 degrees below zero. Minus 196 Celsius, 77 on a scale called Kelvin scale. Look it up. Bottom line is, this stuff is dangerous. It is dangerously cold. So the thing is, though, I went to college. I could play with it all I want because I learned how to do it correctly and safely. If you ever get a chance to be around liquid nitrogen, don't play with it until you've gone to college. I'm serious about that. Anyway, but that means I can have fun with it. So let's do a little experiment, shall we? I'm going to put this balloon in the liquid nitrogen. What do you think is going to happen? But now hang on to that. Don't answer that question. See, scientists do this all the time. They make guesses. They actually have a name for it. They call it a hypothesis. It's a guess. It's a hypothesis. That's the word I was looking for. Anyway, hypothesis is a guess. They make a guess, but then they do an experiment to see if their guess is correct. So whatever guess popped into your head, because by the way, I forgot to tell you this, you're scientists. You're all scientists. You guys make guesses all the time. And then you do experiments to see if your guess is correct. That's what we're going to do. So just watch this. Watch the balloon, see what happens. See if your guess is right. So here we go. Some of you may have thought the balloon's going to pop. Well, it didn't pop. Can you see what is going on? Maybe, I probably have the camera too close in. Can you see what's happening now? The balloon is shrinking. Oh my gosh, it's going to collapse. Look at this. So what's going on in there? Well, we're taking heat energy away from the air in that balloon. That means the little air atoms inside are moving very slowly, which means they're not running into the walls of the balloon very hard. And the balloon collapses down into this sad looking thing. But all the air's still in there. And there's plenty of heat energy out here in the air in the room. So as the heat energy from the air in the room goes back in the balloon, the little air atoms inside start moving faster and faster. They start running into the walls of the balloon harder and harder. The air pressure inside is going back up. Pretty soon the balloon's right back to normal, like nothing ever happened. Ooh. Bye. Okay, I'll retrieve that later. Great question. Oh, you know what? As long as I got the liquid nitrogen out, let's do something else that's fun. Now, I mentioned that liquid nitrogen is dangerous. I'm going to do this down here. Liquid nitrogen is dangerous. One of the reasons it's dangerous is it's really cold, right? If you expose your skin to this for too long, it will freeze your skin and it'll send you to the hospital with something that hurts really bad called frostbite. By the way, I've never been hurt by it because remember, I went to college, I learned how to handle it correctly and safely. There's another danger to liquid nitrogen though too. This one container, liquid nitrogen, if I warm it back up to room temperature, will make almost 700 containers of gas. Let's see what would happen if we try that. Again, expert professional scientists, don't try this at home. So I'm going to take some liquid nitrogen. Got a little scooper here. I'm going to put it inside a container. This is a really bad idea. And I'm going to put a cork on it. That's an even worse idea. Gonna hammer that cork in. Okay? Really bad idea. Whoop. Did you see that? I just shot this cork. I have a target over here to catch that. Want to see it again? That went pretty fast. Let's do it one more time. Okay, 3, 2, 1. Ooh. Yeah, I told you it was dangerous. By the way, if any of you are wondering, these are made of polycarbonate, the same stuff that they use for safety glasses. So I always have safety glasses on. So never, never, never put liquid nitrogen or dry ice, either one, into a sealed container because that kind of thing can happen. And that's a bad thing. Now, I told you earlier the safest place to keep this stuff is in a special container called a dewar. Now, I'm actually, you know what, I'm gonna put the camera back down there. I'm actually gonna spill some on purpose onto the floor just so you can see what it looks like. That's nothing to freak out about. Really? Yeah, because when it spills on the floor, it just makes a cloud. This stuff is so cold, it's actually taking the water in the air around me and turning it into a cloud. That's this white stuff you see. And when it hits the floor, it just turns right back into air. Now, I'm going to pour it back into here, in this container. But I want you to notice what it looks like when I pour it back in. Maybe you've already noticed, but let's take another look at it. Notice what this looks like. Here we go. And by the way, remember, this is the cloud. That's not the liquid nitrogen. What does the liquid nitrogen look like? That's right. It looks exactly like water. Seriously, don't drink it. It will do bad things to your insides. Just don't drink it. Now, watch this. I'm going to close this up. Yeah, that's not a problem. I tell you, this was a special container. It's actually set up so that if any of the liquid inside turns to gas, the gas just leaks out harmlessly. It's not a bomb, okay? I just do that to keep from spilling between shows. I'm going to set that aside. I love the liquid nitrogen question. All right, who's next? Who we got next? Remember, we've still got lasers and high voltage, and I've got fire, and oh my goodness, I've got all kinds of really fun things. So Heather, who we got next?
Looking for some raised hands out there.
Oh, raise your hands, come on. I got cool stuff to show you, but you got to raise your hands up first. Or we'll just pick you at random, I'm not shy.
Everly, do you have your hand raised? Everly, can you unmute yourself, please?
The fire.
Oh, hi Everly.
The fire.
You want to see fire. That's what got me started in physics. All right, I got a couple things that involve fire. I'm going to start with this one right here. I'm going to set my camera up, and I'm going to go behind the table here. So, again, this is the problem of being your own camera person. I don't want to chop my head off. I want you to see my face. Let's see if that'll do. Okay. Kids, seriously, don't. Just don't. Go to college first. Really, if you go to college, you can learn how to do things correctly and safely, and then you can have lots of fun. Don't play with this. Leave this to the adults. Now, what I have here is a blowtorch. You see the fire? Very, very hot. So, one of the things I want to talk about is, we talked about what heat energy is. I want to talk about how you move it around. So there's 3 different ways to move heat energy around. One way is if an atom's moving fast, remember we said that's what heat energy is. And if it bumps into a slower atom, it can get the slower atom moving fast too. That kind of heat energy movement or heat energy transfer, you're going from atom to atom to atom. It's usually most common in metals. It's called conduction. Conduction. Now, don't worry if you don't remember this. It's not a quiz at the end of the show, okay? Conduction. Here's another one. Fire. That fire is a really hot gas. Now, those atoms are moving really fast, right? So when they're moving fast, they like to spread out, right? So wait, if that hot gas is all spread out, it means it's not taking up as much room. That means that the heavier gas comes in and pushes it what direction? You ever seen the smoke from a campfire? Ever seen a hot air balloon? What direction do they go? They go up. So the hot air goes up. Cold air comes in to take its place. It gets hot, it goes up. Pretty soon the air is going round and round like this. This kind of heat transfer happens both with gases and with liquids, so like when you boil water. It's also what makes the weather work. And you may have an oven at home that works on this principle. It's called a convection oven. That process where you're moving heat energy around by moving around hot gases or hot liquids, that's convection. The third one is how when you stand out in the sunshine and you feel warm, that's called radiation. And the weird thing about that is there's no heat energy hitting you. It's light energy, which we'll talk more about later. But light hits your skin, it turns into heat energy you can feel. So conduction, convection, radiation. Now, let's have some fun with this. Oh, I have this tube here. This is a special tube. There's a screen, metal screen in the bottom. I don't know if you can see it or not. Yeah, there it is. It's a metal screen right about here in this tube. This, by the way, is called a hoot tube or a Reiki tube, R-I-J-K-E. I'm not sure I can pronounce it, but anyway, here's what it does. So I'm going to heat that screen up till it's red, red hot. I don't know if you can see it or not in there at this angle. I get it nice and hot. Now, that sound's coming from this. Isn't that fun? What the heck is going on there? Well, we said that hot air likes to rise, right? So that screen's really hot, the hot air rises up in there. And as it does that, goes to the screen, it kind of breaks up in little bits. It's called turbulence. And that sound energy, what we just heard, is actually waves in the air. So it starts creating all these different waves of different sizes. But only one size of wave fits into this tube. Okay, this is, by the way, how musical instruments work too. So that sound wave starts bouncing back and forth, but every time it bounces through that metal screen, it gets a boost, it gets expanded, it gets made bigger. So that sound gets louder and louder until it hoots, like you just heard there. No moving parts, just physics. All right, now, you said you want fire. Well, you know what? I think let's go to another question here. I want to make sure we get, there's lots more stuff to see. So, who's next? That's a great question, by the way. I love playing with fire safely and correctly. All right, Heather? Who we got?
I'd like to see Mike pull something from his bag of tricks here.
Oh, come on. We haven't even got to the good stuff yet, guys. We haven't even got to this table over here. Who wants to see something? And if you don't want to raise your hand, Heather will just pick you. I will.
How about Gavin?
Gavin. Hi, Gavin. Can you take yourself off mute?
Yeah, Lasers.
Lasers. Let's look at some lasers here. Now, by the way, I will probably turn the light. I will turn the lights out here shortly, so don't freak out. It's by design. Anyway, let's set it up like this. Now, first of all, I have worked with some gigantic lasers. Okay, these ain't it. But again, even lasers like these make terrible, terrible toys. So Gavin, can you tell me why? Why are these dangerous?
Not sure.
That's okay. And by the way, not knowing the answer is not a problem. In fact, really, make it a habit and then go find out what the answer is. Lasers like these are so intensely bright that if that shines in your eyes, it could cause you to be permanently blind. Seriously, seriously, don't play with these laser pointers. Don't let your friends play with them. It's not worth it. Okay, go to college. I actually went through laser safety training, so I can play with these all I want. Anyway, so what I got here is I have a red laser. Oops, let me aim this down just a skosh. So I have a red laser. Can you guys see that? I'm going to turn the room lights off. That'd probably help a lot, huh? All right, red laser. Now you can see it. I have a super bright green laser, and I have a wimpy purple laser, okay? Now, I promised a demonstration earlier of modern physics. Modern physics, one of my favorite dead guys, Sir Isaac Newton, father of physics, lived about 300 years ago, which, by the way, explains why he's dead. He came up with a lot of ideas about how the world works, including how light works. And for 200 years, people thought his ideas were it. But 100 years ago, scientists were experimenting with light, and they got results totally different than what he predicted. And I'm going to demonstrate why. Now, I'm actually, you can't see it right now, but I have this in the background. I have a glow-in-the-dark screen back here. Now, you've all played with glow-in-the-dark stuff. Before it will glow, you got to shine some light on it first to charge it up, right? Right, so if Sir Isaac Newton were here, he'd say, hey, shine that super bright red laser thing in there. That'll charge that screen right up. You know, that makes perfect sense. Except I don't see any glowing, do you? I just see the laser, but I don't see that it's charging up the screen. Well, that's weird. Well, you know what? Let's try the super bright green laser here, okay? That bright green laser is so bright, it's not doing anything either. Huh, you know, if Sir Isaac Newton were here, he'd be freaked out right now. That's not what he would have predicted at all. Well, the only one I got left is this wimpy purple laser. Shall we try that? Self-portrait, glasses, beard, eyebrows, nose hair. Yeah, I'm not a very good artist. That's why I became a physicist. But the question is why? Why will my wimpy purple laser leave this beautiful green glowing trail and my green and my red do nothing? The secret was figured out by none other than the most famous scientist you probably ever heard of. And if you said Albert Einstein, you'd be correct. Albert figured it out. He said it's not about how bright the light is. It's about how much energy is in the light. So purple light has more energy in it than green light. Green light has more energy than red. What we see as different colors is really different amounts of energy in the light. And because Einstein figured that out, about 100 years or so ago, it's called an example of modern physics. Now, modern physics, do you like smartphones? Do you like video games? Do you like anything electronic? That's all modern physics and more. We're just getting started with it. There's some really cool stuff happening. So if you're looking to have some real adventures later on in life, go to school and learn about modern physics, because we're talking quantum computers and just all kinds of cool stuff going on. So that is the example with lasers. Thank you for choosing that. All right, who's next? Remember, we still have high voltage electricity, We still have my air cannon to play with. Got some more things over here we could try. What do you think? Heather, you're on mute.
Heather has a vote for high voltage electricity.
So we have two, wait, we have two Heathers, or is that your own vote?
That's my vote.
High voltage electricity, okay. Because what's not to love about high voltage electricity, right? All right, so here's the thing. First of all, we need to figure out what electricity is first, okay? So remember I told you that everything's made out of little teeny tiny things called atoms. Guess what? Atoms are made of even tinier things. And if you could look inside of an atom, you'd see some really tiny things in there. One of the teeniest, tiniest things you'll see inside of an atom are little things called electrons. That sounds like a dead giveaway. So all electricity is little tiny things called electrons moving around. Now what makes electrons special, and there's other things that have this quality too, is they have something called an electric charge. Okay, think of it like a little force field, okay? So it's a negative electric charge. And kind of like with magnets, you know how sometimes you try and put magnets together, sometimes they'll stick together, but sometimes they push apart. So if you put two ends of the magnets that are the same together, they push apart. Same thing with electrons. If you put two electrons next to each other, they want to push apart. Okay? So that's basically what electricity is. It's just those little electrons pushing on each other. Now there's different ways to get them pushing. Here's one way. This is a wind-up flashlight. So it's got a generator in there. So when I turn this crank, what's happening is that there's some little magnets in there that are spinning near a coil of wire. As those magnets spin, the magnets push on the little electrons in that wire, get them moving. Scientists, by the way, call movement energy kinetic energy, but it's movement energy. So those electrons start moving. That energy can then be used to do things like lighting up a light, like this. Most of our electricity comes from gigantic versions of these. That's one way. Now, we said high voltage, right? So I'm actually going to bring the camera in. I'm going to turn the lights off for this one. This, by the way, is called a Tesla coil. Invented by the famous scientist Nikola Tesla. This takes those little electrons and it shakes them back and forth really hard and really fast. So it's high voltage, high frequency electricity. When things are moving back and forth really fast, we call it high frequency. And here's what it looks like. Let me turn the lights off again. Da-da-da. And here we go. You guys see that electric arc? I'm going to bring the camera in just a little bit closer and try very hard not to zap my camera. There we go. That's fun stuff, man. Now, one of the things, okay, so now we know two types of electricity. There's a third type. I'm actually going to set this down for just a second. Third type of high voltage electricity is made with this guy. This is called a Tesla coil, or sorry, this is called a Van de Graaff generator. This makes electricity kind of like when in wintertime when you're rubbing your feet on the carpet and then you touch a doorknob and you get a spark. That's how this works. You can look this up. It's called triboelectricity, but here's what it does. You hear those sparks. Can you see them okay? That looks like baby lightning. Real lightning is made in a very similar way. Of course, this is harmless. It looks really dangerous, but, you know, not going to send me to the hospital. It stings, I won't lie to you, but it's not going to hurt me. Real lightning, on the other hand, is incredibly dangerous. So if you see lightning or hear thunder, get indoors quick. Now, I'm going to show you something really amazing that you can do with high voltage electricity. I used to be a rocket scientist. I'm not kidding about that. I used to work on the space shuttle engines and a lot of other rocket engines. And here's the thing. The space shuttle main engines are pound for pound the most powerful machines ever built by man. They generate 500,000 pounds of thrust each, and they shake the ground. One little problem, they run out of gas in about 7 minutes, okay? So after that, they can't do any pushing anymore. But scientists have created a new kind of engine that uses high voltage electricity. It's called an ion engine, and I happen to have this one set up. So let's watch what happens with this. So what's happening is that, I know, not very impressive, 500,000 pounds of thrust versus ee. But here's the cool thing. So what's happening is that high voltage electricity is coming out the end of the little wires that are at the back end of those little rockets, and it's making the air electric. Electric air is called ions, and those ions are pushed away from the other electrons, and then, so the ions shoot out the back just like the exhaust from a rocket engine. And by something called Newton's third law of motion, for every action there's an equal and opposite reaction, the rocket moves forward. It's also called the law of rockets. Now, not very impressive, but what really is impressive about it is that you can run this kind of engine for years, not minutes, not hours, years at a time. So even though it doesn't push very hard, it adds up. Someday we're gonna send scientists to Mars, might even be you. Using regular rockets, that trip takes almost a year, like over 300 days. If we can figure out how to make those kind of rocket engines work, the trip might take 35 days. Can you imagine being cooped up in a rocket ship for a year? Are we there yet? Drool coming down? I vote for the 35 days, okay? So, great questions on high voltage electricity. All right, Heather, do we have any time for maybe one more demo, or?
Sure, Mike.
Yeah, we've got a few minutes left here, so.
Anyone in the audience?
There's some people in the audience I haven't heard from. Aiden and, let's see. I don't think, Aiden, have we heard from you? Would you like to choose something? No? Okay. Well, you know what? One thing I haven't shown yet is this guy. This is my air cannon. I'm going to move my camera just a little bit closer. This actually is a conversation about energy. I told you earlier that energy is what makes things happen. There are many different forms of energy. But they all have two weird things in common, okay? You cannot make energy. You can't do it. You can't get rid of it either. You can only turn it from one form into another. And that's what we're doing right now. You hear that pump in the background? That's turning electrical energy into using electrical energy to squish the air, to compress the air. So we're storing up energy. That's called, scientists would call that potential. We're storing that squished up air in this tank right here. So we're storing energy. When we store up enough energy, I can let it all out. This will take a little bit. So I'm going to push the trigger. It's going to let all this air out all at once into a cannon. I've got one of my friends here, one of these guys, already loaded up in there, okay? By the way, again, don't try this at home. You might even find websites that tell you how to make these. Most of the things that you find on the internet are dangerous, that they didn't really think them through well. This one has been designed by professionals, me, other people. It's very, very, very safe. And you don't want to just aim it in any random direction. You ready? 3, 2, 1. Whoop, there it goes. Oh wait, I found it. It ended up back here. Yeah, check it out. Yeah, you'd look like this too if I shot you out of a cannon. That's like the 4th generation. I actually designed that one to be something I could fly with. I actually travel around the country and I do shows. And it was either drive for 3 days each way with a trailer load of equipment or figure out how to pack it all into some bins and fly with it. So that's my flyable version. It's one of my new favorite toys. All right, we have, let's see, we've got a few more minutes. Oh, one thing, oh, you know what? You like explosions, don't you? I know I forgot something. So right over here, we're talking about uses, talking about high voltage electricity. One of the uses for it, oddly enough, is inside your car engine. So your car engine runs, most cars these days don't run on electricity, at least not yet. They run on car fuel. So I've got a tiny little bit of car fuel in here. It's called ethanol. You can run cars on it, but it doesn't do anything unless you light it on fire. Now, do you think electricity is hot? By the way, I didn't show you this toy either. This is called a Jacob's ladder. Can you see that spark of electricity there? This is something they used to use in old 1930s sci-fi movies as a special effect. The reason that spark keeps going up is it starts at the bottom because the wires are closer together down here, but then it's hot. It's like hot air. Hot air rises, hot plasma rises. Plasma is what they call electrified gas like this. So that gas rises up until it gets so wide it breaks, and then it starts over again at the bottom. But it's very, very hot. What does that have to do with this? Well, we have to light that fuel on fire, right? Hey, if a spark is hot, that sounds like a good way to do it. So we have a spark right here in the Tesla coil. Let's see what happens when I put a spark in here. Ready? 3, 2, 1. Ooh, bang. Makes an explosion. What does it have to do with your car engine? Well, like you said, in your car engine, you spray car fuel in, you light it on fire, it makes an explosion, which pushes on a piston, and eventually makes the wheels of the bus go round and round. That happens hundreds of times every second. All right, 10:43. Oh, you know what? I've got time enough maybe for one more demo here, since I have this out. Remember I told you about how airplanes work? This is really fun. This is a version of it. What would happen if this is curved on top, so what would happen if I blow air over the top of this? Let's see what happens. This is one you could try at home. Just a little inflatable beach ball and a leaf blower. So why was it just hanging there? Well, I told you about forces earlier, right? So the reason it wasn't moving around much is that the forces were in balance. When I put the air over there, the air underneath was pushing it up, but what was pulling it down? You guys all know this. Gravity, right? We balanced gravity with the air pressure pushing up, and it just hung there in the air. Very much like an airplane does. All right. I have 10:45. Oh, one thing I want to leave you with before we start the questions. Look, the reason I do these shows, I wish you were here in person. Yeah, it's just the way it is for now. I do. But what I want to leave you with is that you are scientists. You are physicists. Your whole world is about physics. Everything you do is physics. And understanding how your world works gives you power. Let's say the Olympics, for example. You know, the Olympic athletes study physics. They seriously do. Because by knowing physics, they could actually improve their performance. They can be better athletes. And that could be the difference between winning a gold medal and not winning a gold medal. But it's not limited to sports. It could be any part of your life. What do you like to do? Do you like cooking? I've done shows on the physics of cooking. Do you like music? I've done shows on the physics of music. Do you like dancing? I've done shows on the physics of breakdancing, okay? Really, whatever you like to do, if you understand how your world works, you could be better at it. And here's the last thought I want to leave you with. If you're doing better at something you like to do, doesn't that mean you're having more fun? I think that's true. I have a ton of fun doing these shows. So thank you. And I thank you and I thank Monona Terrace for providing me the opportunity to keep doing what I do. Thank you so much. Now, shall we answer some questions?
We do have a few questions for you.
Yes, please.
What will happen if you make the fire touch the liquid nitrogen?
What would happen if you make the fire touch liquid nitrogen? Huh. Well, I don't know that I want to put the fire into it. It could actually explode out. Now, it would just splash around the room, which is, you know, if you know what you're doing, that's not terrible. But I think I've got enough in here. Let's do a little experiment. But I'm not going to use the fire. I'm going to use something else. I'm going to bring the camera in nice and close here. I'm going to use my finger. My finger's warm. Remember, that's 321 degrees below zero. My finger's probably, I don't know, 90 degrees. So it's like let's say it's about 400 degrees. My finger is 400 degrees warmer than that stuff. Now imagine if you took a 400 degree or 500 degree piece of metal and shoved it in water. What's it going to do? Water's going to boil like crazy, right? So watch what happens. Well, by the way, my finger's fine. And what happened is it boiled. The reason my finger is fine, by the way, don't ever try that, because if you do that wrong, it will send you to the hospital with frostbite. My finger is warm enough that when I stuck it in there, it made a layer of gas. Some of that liquid instantly turned to gas. And that gas doesn't carry heat energy very well. So it actually protected my finger for a moment or two and allowed my finger to be fine. And there's actually a name for that. It's called the Leidenfrost effect. Don't ask me to spell it, but try and look it up. It's different pronunciations, but I think the correct one is Leidenfrost. Good question. What's another one?
I have a question from Chris who asks, how cold can matter become?
That is a really good question. There's an ultimate limit, okay? I mentioned the temperature scale earlier. I said 77 Kelvin. Kelvin scale is the same as the metric scale, like the Celsius, only its 0 point is at something called absolute zero. Absolute zero is the theoretical temperature where atoms stop moving. Now here's the thing you need to know about atoms. Atoms move. Atoms always move, always. Now, scientists have special tricky ways that they can get the atoms very, very close to absolute zero. In fact, using lasers, that's a whole nother topic. But you can actually use lasers. So if an atom's moving into a laser beam, if it moves toward the beam, it slows down. And so they call that laser cooling. You can look that one up. But you can get to within a few millionths of a degree of absolute zero. They've done that in the lab, or maybe even colder than that. But you cannot get to absolute zero because there's really no way that we know of to make atoms totally stop. So that theoretical temperature would be 0 degrees Kelvin, which is minus 459 degrees below zero, I believe is the temperature in Fahrenheit. It's minus 273 Celsius, okay? But that's a really, really good question. Okay, next question.
You were starting to get at this, I think. Owen asked, is it possible to cool atoms down to the point where they stop moving?
Well, I just answered it. So the actual answer is no. Now, I mentioned quantum physics. I mentioned modern physics earlier. One area of modern physics is something called quantum physics. Is that when atoms, down at the atomic level, atoms act in very weird ways, which is what makes modern physics work. It doesn't, you know, they can do things like jump through walls. They can be in two places at once. It's mind-blowing, okay? It is possible to get atoms actually at or below that temperature I told you, but it's kind of a quantum trick. In reality, in terms of the world we're familiar with, you cannot get to absolute zero, but you can get very close to it.
Thank you.
And when you do, by the way, scientists do this all the time, because when you get atoms that cold, that quantum stuff that I was mentioning, that kind of takes over and really weird things can happen.
Rebecca asks, what kind of physics are used in cooking?
Remember we talked about heat energy? Conduction, convection, radiation, that's it. All three of those are the physics in cooking. Now, there's some other things too, but if you're cooking something, you're putting heat energy into something. So if you're frying in a frying pan, you have a metal frying pan, that metal takes heat energy, it puts that into the food, that's conduction. If you are baking something in the oven, particularly a convection oven where you've got warm air swirling around, that heats the food, that is convection, and like in a convection oven. By the way, boiling water is also convection, where the water is swirling around the food and heating it up. That moving water is what carries the heat energy. And then I mentioned the third one, radiation. That would be like broiling, like if you put something under a broiler, or your microwave oven, by the way, also uses radiation. It's using a different, it's not using light. It's using a kind of radio wave that makes the atoms, particularly the water atoms and something, jiggle back and forth. So that energy goes in, that electromagnetic energy is the technical term, but it's just like radio energy goes in, and then the water atoms turn that into movement energy, wiggling around, which is what we call heat energy. So conduction, convection, radiation, very cool stuff.
We have a question about, when did you find out, Mike, that you like science?
I was very lucky. My father was a scientist. He had me doing science projects from like the earliest time I can remember, okay? I remember in kindergarten, I did a whole science project on magnetism, and he helped me with it, okay? But still, it got me excited. I got excited early on. And so that's been my passion ever since. It's like, I've just never not wanted to be a scientist, because scientists get to do so many cool things. Did I mention I used to be a rocket scientist? Seriously. I actually got to do experiments where they have when they fire a rocket engine in a test stand, they have a special super reinforced building called a blockhouse that's 700 feet away from the engine. That's the closest you're supposed to be. I actually did experiments in front of the blockhouse, like out in the open, where I had a telescope aimed on the rocket flame. It was a special infrared telescope, so I could actually see what the rocket flame looked like in a different, like in light that we can't see. Infrared is a different light band that's tells you more about heat energy. Anyway, very cool stuff. I've also got to play with big lasers, like lasers that are like 1 million times more powerful than those laser pointers. And I could go on and on. But yeah, it's like really, it's so, the more I got into it, the more excited I got. And now I want you to be that excited too, because it's like, your parents may not be scientists, but really I want you to get, there's so much cool, fun stuff happening. And the more you understand your world, the more power you will have, and you'll make better choices in your world too. And that's also very important. Okay.
Mike, we've got a request for explosion. The question is, with liquid nitrogen, could you put it in a water bottle and let it explode?
Yes, people do that. In fact, go on YouTube and look this up. Don't try this yourself. I'm so serious. It's incredibly dangerous if you do it wrong. But the way to do it that you'll see online is that people will take like a little soda bottle, maybe even smaller than one of these, and fill it full of liquid nitrogen. And the smart thing to do is then like have a big 55-gallon trash can, like a plastic trash can full of water. So you take that bottle, you weight it down, and you drop it quickly in the water, and then you run away. I'm not telling you this for you to try it. Don't try it. Watch people do it on YouTube, and maybe they do it right or not, but don't attempt it. Anyway, as that liquid inside turns back into a gas, did I mention it expands like 700 times? That's a huge expansion. Well, that bottle is very strong, but it can only hold back so much. At some point, the bottle gives way, bang! And I've seen videos, I've seen this done where not only does it shoot water everywhere, it actually blows the trash can into pieces. Okay, even from just a little bottle of liquid nitrogen. Really seriously, I cannot stress it enough. Don't try that. And don't try it with dry ice either. It's not as big a bang with dry ice, but it's still quite dangerous. The truth is, if people do try that and the police find out, they will come arrest you, because what you're building is a bomb. And it's a particularly scary kind of bomb because you have no idea when it's going to go off. So just don't do it. Leave it, or go to college and learn how to do it correctly and safely, okay? But don't just go out randomly trying that, okay?
We have 2 questions about rockets, so I'm going to ask them both in case they're related. One is, how fast would the ion engine go when it was in a rocket? And the second one is, how does a capsule eject from a rocket?
Let's start with the ion rocket. How fast you go really it depends on two things. It depends on how powerful the engine is, and also depends on how long you let it run. Scientists, you look up impulse. So that's a term that's used in rockets. It's about how hard are you pushing and for how long. They call that impulse or specific impulse. So how fast you get going, just if you have a rocket engine that's really powerful, which we don't have them yet, we're working on it. So I mentioned you could cut the travel time from Mars from 300 days to like 35 days. So you can cut it by 10 times. So I don't, a regular rocket engine going to Mars might be going using regular rockets like the space shuttle rocket engines, might end up going, I don't remember the exact number. I'm going to say 30,000 miles an hour, 40,000 miles an hour. So you can imagine how much faster you can go. There would be an upper speed limit on it in terms of, just at some point that you still have to carry some fuel along. You have to have something that's shooting out the back. But the real future of space exploration is in ion engines, because that'll cut the time down, like to explore Mars or even go beyond Mars, down into times that can reasonably be handled by human beings. But I don't have a number for you, but look it up and let me know.
We want to thank you.
Oh, the other one was about ejecting a capsule. They use an explosion. They have special explosives that fire. They're called a shape charge, where they will fire in a particular direction. So you're talking about ejecting the parachute, or are you talking about just separating the capsule from the rest of the rocket? So if it's setting out the parachute, it's a special explosive. And for separating the capsule from the rest of the rocket, that's explosive bolts. They actually have special bolts with little explosives inside that when they fire it off, the bolts basically disintegrate without causing any damage to the surrounding area. But it's very reliably, very quickly separates the two.
Thank you. One last question. We want to thank everybody for their questions today. One last one from Leslie. Do you have any parabolic dishes you could show us?
I have parabolic dishes, and they're not where I can show you. I used to do a demonstration, and maybe I'll resurrect it if people want to see it, where I used 2 parabolic dishes and a heat source. So it's a demonstration of radiation I talked about earlier, where I'm taking light energy from I have a source that's just basically some coils of wire that get red hot when you put electricity into them. That gives off light energy. Anything that's warm gives off light energy. Now, it's not always light energy we can see. Some of it's called infrared light. Anyway, that invisible light energy bounces off that dish, goes over to another dish, and the dish refocuses it onto a match head. Now, if I get it lined up right, I can set off a match head from 6 feet away using parabolic mirrors. Now, other places you'll see them, if you have a dish antenna on top of your house, like to get your cable TV, that's a parabolic antenna. So it takes radio waves from outer space and focuses them onto a receiver so you get a nice strong signal. That's the more common place you'll see it, but it's a really good question. So maybe I'll dust off my parabolic mirrors and bring them in for another show.
Applause, applause, Mike. Thank you so much.
Yay. It's been my pleasure. I really love doing these shows. Oops. And I love not spilling my liquid nitrogen.
Well, we want to thank our audiences for joining us today, and thanks to our wonderful Monona Terrace AV staff. See you on Wednesday, August 12th for Lakeside Kids Butterfly Exploration at Olbrich Gardens. Thanks, everyone.
Yay. Thank you.